Hello people, welcome back to the corgi64 project where we're building a simulated computer from scratch. Where we last left off, we were at our main program and we were trying to figure out how to write main memory or write the memory of our program in an easy way. I think what we'll end up having to do is just write out the bytes manually, all the bytes that we need. So in this episode, though, we're actually gonna fix some bugs. We're gonna do some cleanup, and we're going to set up the proper way to do fetching of our instructions, because it turns out there's a bug. Now, a lot of the things I'm going to address today, I actually got a pull request for on GitHub from Johan150. So thank you very much for your pull request. A lot of the things that you mentioned were things that I'm going to deal with today, so let's go ahead and do that. So let's go ahead and go to, actually the first thing that we'll go ahead and do is we'll create a proper way to print out the status of our CPU. Right now I wrote this just as kind of a placeholder. That's just kind of junk that we're going to throw away. So let's go and write a CPU print function that will allow us to have proper printing of our system. So let's do CPU print status, and we'll get a pointer to our CPU, and what we'll do is we'll have a printf, and we'll print out all of our registers. So the A register is LLD, the B register, we'll print out the C register, and then we'll print out the program counter and the stack pointer, and the flags register. And what we'll do is we'll print out all of these things. So we've got A, B, C, program counter, stack pointer, flags. And that takes care of the print function. The next thing that we'll do, actually the other thing that I neglected to do last time was to set up our halt instruction. So if you remember, we created our halt instruction up here, but we never put it in our opcode table, so it's unaccessible to our CPU when it's trying to run it. So if we go down here, we'll see that the halt instruction is 2E. So we'll go back to our table and go to 2E and replace the no-op with the halt instruction. So that fixes that. Now the next thing that we want to do is we want to get the proper way to access our memory. So if you remember, back down here in our run instruction, we actually cast the place in memory to an instruction, and it turns out that this will not work the way we want it to. And the reason why is the way that the compiler does padding for structures. So if we look back up here at our instruction struct, in memory, what we'll have is it'll have one byte and 7 bytes. And then it will have 8 bytes. And so the 1 byte will be for our opcode, and then it will actually add 7 bytes of padding, because the way that structs like to access the members is to have everything perfectly aligned, so that way when you do an add, or the way that in memory instructions or structures, the fields and structures are accessed, is they're accessed through offsets. So the first field in a struct always has an offset of 0. And the next field will be some offset. And the way that the compiler likes to do things is it always likes to have the same offset number for everything. So that way it's some multiple of an offset. And usually it's of the largest size of the value that we've gotten. So this is 8 bytes. So we need to be 8 byte aligned, which means that what the compiler will do is it will add 7 bytes of padding onto this instruction in memory. So you can think of this as kind of like a line. It's not really, but you can think of it as a line. It'll have 1 byte, 7 bytes, and then 8 bytes. So that's not what we want. We want to have 1 byte and 8 bytes. So what we'll do is we'll actually write a function that will fetch our instruction for us and do the proper pulling from memory. So let's write CPU fetch, and we'll give it a pointer to our CPU. And what we'll want to do is we'll have our C instruction opcode, and that's going to be equal to let's see, what do we want to do? We want to have our C memory, and we want to have the offset, which is the program counter. And so our memory is already of type byte, and our opcode is of type byte, but we're going to get that place in memory, that pointer in memory, and dereference it. And that will give us the value of the opcode. So then for our value is 8 bytes. So what we're going to want to do is cast this to an i64 pointer, and we'll add our offset +1. So the way that this works is we have our pointer to our memory, we add an offset for where our program counter is, and we've already read this byte, so we want to read 1 byte after. And casting it to an i64 pointer allows us, or tells our computer that we want to read 8 bytes. We don't want to read 1 byte, we want to read 8 bytes. And then when we dereference it, we'll actually put that value into our instruction register value. And so that's how we're going to fetch our system. We could have set it up where we padded all of our instructions, but then we're just going to waste a whole bunch of memory. So this, I think, is a much better way of doing it. So if we come back down here, what we'll do for our fetch and decode is, instead of setting the C instruction, we're going to do CPU fetch. And we'll give it our pointer to our CPU, and that will set our instruction. Now the next thing that we want to do is just incrementing our program counter by 1 is not going to work, because sometimes our instructions are 1 byte long and sometimes they're 9 bytes long. So we need to actually increment our program counter by a specific amount. And it's actually based upon the function that we're running. So some of these, like add and subtract and multiply, are just 1 byte instructions. Some of them, when we have set a register to an immediate value, that's going to be 9 bytes long, because it's going to have setting the instruction to A, and we need to actually add the immediate value that we need. So what we're going to do here is we're actually going to copy this table of opcodes, and we're going to have a new table. Actually, I need all of it. We're going to create a new table, and this will be a table of memory offsets. So this will be our let's see, we'll just call it our offset table. And what we'll do is it'll have the same sort of things, but instead of having functions in here, what we're going to do is we're going to have the offsets that we need for our program counter. So what we're going to do is we're going to look through here in our selection. We're going to find all the new ops, and then we're going to replace them with 1, because the standard for everything that we're going to have is 1. And actually, you know what? Let's undo that. Let's do a find our selection. Since everything was 3 wide, what we're going to do is we're going to say, okay, we're going to find all the no-ops. Okay, we actually want to find only in selection. So let's do select, find, in selection. We're going to find all the new ops. We're actually going to replace it with 0, 0, 1. So that way we're always using 3 characters. Do a replacement, and there we go. So now we've got 3 characters. Hopefully this doesn't mess up. Hopefully it doesn't think that these are binary numbers or anything like that. We just want 1. If it does mess up, we'll fix it. But what we're going to do is for each one of these things, we're going to say whether it's 9 bytes or 1 byte. So our standard is 1 byte. So, but setting these will be 9. And add, subtract, multiply, and divide, and mod will be 1. And then halt will also be 1. Now let's go down here, and what we're going to do is, instead of incrementing our CPU counter by that, we're going to say we're going to increment it by our offset table. And we're going to say we're going to get our C instruction opcode. Our opcode will tell us where we are in our offset table, and it will allow us to increment our program counter by the correct number of bytes. So that should take care of that. The next thing that we want to do is go back to our main program, and we want to write a program that will actually run on our system. Actually, what we'll do really quickly is replace this old print statement with CPU print status, and we'll give it our CPU. And now we can write our memory. So what we'll want to do is we'll take this. This actually needs to be an array since we're using an initializer list. And what we're going to do is we're going to make this a little bit more readable. We're going to put comments on here. So this is going to be store or set immediate value in register A. Then since we're writing the bytes ourselves, we actually have to know the Indianness of our machine. I happen to know that my machine is an Indianness of Little Indian. So what we're going to do is pad it with some zeros. Whoops. And so we've got 2, 3, 4, 5, 6, 7, 8. So that gives us our 8 byte padding, and so that way our least significant number, our least significant byte goes first. This will be SIB for storing an immediate value in the B register. Then we're going to store 4 there, so we'll be able to take everything that we did here and copy it down. 16 is add, and 2E is our halt instruction. So now we have memory set up. Maybe we'll line all this stuff up so it makes sense. And what we'll do is now we have our actual memory that we can run. Let's go back over here. There was actually a couple other things that we wanted to do that I left out last time. And one of them was initializing the CPU. Let's initialize the C register to 0. And for resetting the CPU, we'll set C to 0. And I think that's okay. So if I haven't made any, let's see, if I haven't made any mistakes, what we should be able to do is run our build.bat. Illegal 9 for base 8. So I actually have a few mistakes that we need to fix up. So CPU 94, illegal digit 9. So let's go to CPU 94. That's what I Oh yeah, okay. So this is what I feared. So actually having a 0 in front means that you're actually an octal number that you want to do. So I use a lot of different languages, and apparently the C language, when you put a 0 in front of here and it's not an X, it's going to want to write things in octal. So what we're going to do is, okay, what we'll do is we'll do a find. In this selection, we'll find all the 001s. And what we'll do is we'll replace it with space 1. Hopefully that will work. There we go. So now we've got ones. Now we've got decimal ones. And then what we can do is just do manual 9s here. Now everything still lines up. Be able to save it, do a build. So now we can focus on some of the other things. So in line 110, initializing cannot convert from int to void CPU star. Let's see, take a look at that. Line 110. Oh, yeah, we don't want CPU star here. We actually all we want to do, let's see, offset table 256, CPU, we're actually going to pass it a number, an i64, instead of a CPU. And what we're going to do is we don't need to pass it anything, I don't think. Because what we're going to get out the other side is opcode, optable, instruction opcode, instead of the CPU. Oh, we're not going to execute the opcode table. We just want to access the inner parts of it. So we're going to get this local void opcode. This will be a pointer to an offset table. Actually, what we'll do is, it doesn't even need to be a void star pointer, it just needs to be a, will be a table of i64s. And we will initialize it with those. Okay, so now we have our opcode table. Don't need that anymore, so we're going to do the build, and we've got a successful build, so let's try running it and see what we get. Okay, so it looks like we actually have a little bit of a problem, so let's go take a look. I bet it has to do with how we're accessing our memory from this opcode table. Oh, so this op table, whoops, okay, this needs to be, this actually needs to be our op table. We're going to be executing this thing. I was actually changing the wrong thing, so let's take a look at that. Let's see if we do a build and a run, now it works. So if we think about what our program was going to do, A was going to be filled with 3, B with 4, and then when we add them together, we store that in A, and that gives us 7. So that actually does what we want. Our program counter ended up being 20, which is what we want as well. If we go actually back over to our main CPU, if we think about this, okay, this starts at 0, so 0, we're going to have 8, 9, 17, 18, and 19. And the reason why we end at 20 is because of how our run function works. So if you think about it, once we fetch our, let's say we fetch our last instruction at 19. So we're going to fetch that instruction, and then we're going to increment our program counter by 1, which will be 20. and then we'll look at our opcode table for our opcode, and we're going to say, oh yeah, let's see. Oh yeah, then we're going to execute our instruction that we've got. So what will happen is, even though this goes to 20, it's never executed at 20 because once it goes back around, we've executed our halt instruction and we're no longer running, so we'll never do a fetch at 20. So that actually takes care of that. And I think we're at a good stopping point right now. Now we actually have everything set up. We've got the CPU actually running and reading instructions. So next time we'll be able to actually add more of these instructions and get more things underway. So thank you for watching. Till next time.